Right now, inside every atom of your hand, something impossible is happening. The tiny particles you were taught are solid little balls are barely there at all. Weigh one and almost all its mass goes missing. Look closely and it dissolves into a ripple in an invisible ocean. Tonight we go down to the deepest layer of matter, where empty space roars. Particles borrow energy from nothing, and your own weight turns out to be trapped light. If this journey thrills you, a like or subscribe helps enormously. Prepare yourself. We begin. Close your eyes and picture the smallest piece of yourself. Go smaller than a cell, smaller than a molecule. Keep going until you reach a single atom and then dive into its very center. What do you see? Most people see the same thing, a tiny hard ball, maybe a cluster of tiny hard balls, packed together like marbles in a bag, sitting still, waiting. That picture feels obvious. It feels like common sense, and it was taught to you on purpose, because for a long time it was the best answer anyone had. The idea is ancient. More than 2,000 years ago, a Greek thinker named Democritus asked a simple question while looking at an ordinary object. If you take a piece of cheese and cut it in half, then cut that half in half, and keep going, does it ever stop? He decided it must. Eventually, you would reach a piece so small that no knife in the universe could ever split it again. He called that final piece the atom, which means the uncuttable. And for most of human history, that single word held the deepest answer anyone had about what the world is made of. For over 2,000 years, that was the whole story. Matter was made of tiny, solid grains, and the grains were the end of the line. Hard, permanent, real. The floor of reality, that single mental image, the solid grain, is the picture we are going to take apart tonight, piece by piece. And by the end, almost nothing about it will survive. Here is the first crack. Those grains you are imagining are mostly hollow. If you could blow up a single atom to the size of a giant sports stadium, the heavy center, the part that holds nearly all the weight, would be smaller than a marble sitting on the very center of the field. Everything else, the entire roaring space, out to the top row of seats, is empty. Nothing fills it. A single grain of your fingernail is more vacant than the space between the planets, a tiny speck of heaviness lost in a vast, silent hollow. So the solid table under your hand is a lie, your senses tell you. Your hand feels resistance. It feels a smooth, hard surface. But that surface is a swarm of almost totally empty stadiums. And the reason your hand stops is not that it hit anything solid. We will get to the real reason, and it is stranger than any wall. Think of what this means. The chair holding you up, the ground under the chair, the mountains and oceans and every person you have ever hugged, all of it is built from grains that are nearly all empty. The universe of solid things is a magic trick, played on a scale too small to see. And it gets worse for the marble. Because when scientists finally built machines powerful enough to look inside that tiny central marble, to see what the grains were truly made of, they did not find smaller marbles. They found something that has no business existing, something that flickers, spreads, and refuses to hold still. To understand how deep the strangeness goes, we first have to break open the atom ourselves. At the end of the 1800s, the atom was still a mystery box. Everyone agreed it was there. Almost no one agreed on what it looked like inside. One popular guess imagined the atom as a soft ball of positive charge, with tiny negative specks stuck in it, like raisins pressed into a lump of dough. Then a team in England decided to shoot at it. Their leader was Ernest Rutherford, a booming, restless New Zealander who loved experiments that gave brutal, clear answers. His plan was simple and violent. Take a sheet of gold hammered so thin it was nearly see-through, then fire a stream of tiny, fast, positively charged bullets straight at it and watch where they went. If the raisin dough picture was right, the answer was easy to predict. The soft, spread-out atoms would barely nudge the speeding bullets. Every shot would punch through almost dead straight, like throwing pebbles through fog. Most of them did exactly that. They sailed through the gold as if it were empty, which, as we now know, it very nearly is. But then came the result that made Rutherford's jaw drop. Every so often, a bullet came screaming back, not deflected a little, fired almost straight backward, as if it had smacked into a wall. He later said it was the most incredible thing that had ever happened to him. It was, in his words, as strange as firing a large shell at a sheet of tissue paper and having it bounce back and hit you. Sit with how bizarre that is. Thousands of bullets passed through untouched, and then one rockets backward off something invisible. There was only one way to explain it. The atom was not a soft, spread-out ball at all. Nearly all of its mass and all of its positive charge was crushed into a single, unbelievably tiny lump at the very center, a lump Rutherford named the nucleus. The bullets that came back had scored a direct hit on this hidden heart. The rest sailed through the vast, empty space around it. This was the birth of the modern atom, a dense core at the middle, holding almost all the weight, with lightweight electrons somewhere out in the surrounding void. The stadium with the marble at its center, and for a while, it looked clean and final. The nucleus was the new uncuttable grain, the true solid speck at the bottom of everything, the answer Democritus had been reaching for all along. That comfort lasted about as long as it took the next generation to look closer, because the nucleus itself turned out to be built from smaller pieces, protons and neutrons, and the protons and neutrons were built from smaller pieces still, called quarks. Every time scientists found the flaw had a trapdoor. So, we are left chasing the same question Democritus asked, only sharper. Is there a smallest piece, a final grain, or does the cutting never truly end? To answer that, physicists went after the lightweight speck orbiting the outside, the electron. It seemed like the simplest thing in the whole atom, a tiny point of charge. Easy. And it became the doorway into a nightmare that would rewrite what a particle even is. The electron looked like the safest bet in physics. A tiny grain of negative charge, far smaller than the nucleus, zipping around the outside of the atom. If anything deserved to be called a simple, solid point, it was this. So scientists set out to prove it, using one of the oldest tests known for telling a particle apart from a wave. The test is a wall with two narrow slits cut side by side and a screen behind it. Send tiny grains at that wall, like a spray of sand, and the answer is boring. Sand pours through the two slits and piles up in two stripes on the screen behind, one behind each slit. Grains make stripes. Simple. Now send a wave instead. Drop a stone in a pond and let ripples roll toward the wall. Each slit becomes a new source of ripples, and the two sets of ripples spread out and cross. Where two peaks meet, they add into a tall peak. Where a peak meets a dip, they cancel into flatness. On the screen behind, you get many bright bands and dark gaps. An alternating pattern, waves make many stripes. So the experiment gives a clean verdict. 2 stripes means grains. Many stripes means waves. Fire electrons at the wall, count where they land, and settle the question forever. They fired the electrons. The screen lit up with many stripes, the pattern of a wave. That was strange, but people could imagine an answer. Maybe the electrons were bumping into each other in the beam, jostling like a crowd, creating the pattern by accident. So the scientists did something clever and cruel. They turned the beam down so low that only one electron crossed the machine at a time. One lonely electron, then a long pause, then the next. Nothing to bump into, nothing to interfere with. Each single electron struck the screen as one tiny dot, in one spot, like a grain. Good. That felt safe again, but they let it run. Dot after dot after dot, one lonely electron at a time, each landing somewhere that seemed random. And slowly, out of thousands of separate dots, a picture built itself on the screen. Many stripes, the wave pattern, bright bands and dark gaps, assembled one single grain at a time. Read that again slowly, because it is one of the deepest facts ever discovered. Each electron went through the wall alone, with nothing to interfere with. Yet each one somehow knew to avoid the dark gaps and favor the bright bands, as though it had passed through both slits at once and rippled against itself before deciding where to land as a single dot. The electron behaves as a spread-out wave while it travels, and as a tiny grain when it arrives. It is both. It is neither. It is something we had no word for, because nothing in the everyday world does this. The marble is dead. Whatever an electron is, it is not a small hard ball flying through space. And if the electron, the simplest particle we had, is this strange, then the heavy heart of the atom, the proton, was about to break the picture even more violently. Because when scientists tried to do the simplest possible thing to a proton, add up its weight, the numbers fell apart. Here is a calculation so simple a child could do it, and it gives an answer so wrong it took the greatest minds in physics decades to explain. Take a proton, the heavy particle sitting in the heart of every atom in your body. Deep inside it are 3 even smaller particles called quarks, 2 of one kind, called up quarks, and 1 of another kind, called a down quark. 3 little pieces locked inside. Now do the obvious thing. To find the weight of the whole proton, add up the weights of its pieces. This is how weight works everywhere in your daily life. A bag of groceries weighs as much as the groceries inside it. A wall weighs as much as its bricks. So weigh the 3 quarks and add them together. Scientists have measured those quark weights with breathtaking care. Add the 2 ups and the 1 down, and you get a small number. Call it the pieces total. Then go weigh the actual proton in the laboratory. The real thing. The real proton is about 100 times heavier than its 3 pieces added together. Stop and feel how insane that is. The parts add up to 1, and the whole thing weighs 100. 99% of the proton's weight is simply not in the pieces. It is missing, absent from the calculation, gone. This is not a small error that a better measurement will clean up. It is not a rounding mistake. Nearly the entire weight of the proton comes from somewhere the 3 quarks cannot explain. Now, make it personal. Protons and their partners, neutrons, carry essentially all the weight of every atom, and atoms make up you. So this missing 99% is most of your body weight. It is most of the weight of the chair, the floor, the mountains, the oceans, the planet, and the Sunday. The overwhelming majority of the weight of everything you have ever touched comes from a source that the simple pieces added together picture cannot account for at all. Imagine weighing a suitcase, opening it, weighing every single thing inside, and finding that the contents make up only 1% of what the packed suitcase weighed on the scale. You would be stunned. You would tear the suitcase apart, checking the lining, searching for the hidden 100-fold weight. That is exactly the situation physics found itself in, staring at the most common particle in all of ordinary matter. So where is the weight hiding? It is not more quarks, because we have counted them. It is not some secret heavy grain tucked inside, because we have looked. The answer, when it finally came, was stranger than any hidden object. The missing weight is not a thing at all. It is a storm, a furious, invisible storm of energy raging inside the proton, and that storm has weight all by itself. To understand how a storm can weigh something, and how energy can become the heaviness of solid matter, we have to throw out the last piece of the marble picture. We have to stop believing that particles are things, because the deepest truth of matter is that particles are not objects. They are disturbances in something that fills all of space. We have watched the solid marble die 3 times now. Empty atoms, an electron that spreads like a wave, a proton whose weight comes from nowhere the pieces can explain. Every time we look closer, the idea of a tiny hard ball dissolves in our hands. So, physicists made a radical move. They stopped asking what tiny object a particle is and asked a completely different question. What if a particle is not an object at all? Here is the answer they arrived at. and it is the beating heart of everything that follows. Fill all of space, every last corner of the universe, with an invisible substance, not air, not water, something far more fundamental, spread evenly through every point of the cosmos at once. Physicists call this substance a field. Now, most of the time, the field sits calm and flat, like the surface of a perfectly still lake stretching in every direction forever. And a particle, an electron, a quark, any of them, is simply a ripple in that lake, a little bump of energy traveling across the surface. That is all it is. The electron is not a grain flying through space. The electron is a ripple in a thing called the electron field, a field that soaks every point in the universe. When you see an electron move, you are watching a wave move across an invisible ocean, the way a wave rolls across water without any single drop of water traveling along with it. This one idea untangles the nightmares we have already met. Why did a single electron pass through both slits and ripple against itself? Because it was a wave in a field the whole time it traveled. Waves spread. Waves go through both openings. Waves interfere. Only when the ripple slammed into the screen and dumped its energy into one spot did it look like a grain. The electron travels as a wave and lands as a dot because it was a ripple wearing a disguise. And there are many fields, one for every kind of particle, an electron field filling all of space, whose ripples are electrons, a field for each type of quark, whose ripples are quarks, a field for light, whose ripples are the little packets of light we call photons. The universe, at its deepest layer, is a stack of invisible oceans laid over one another, everywhere at once, and everything you have ever seen or touched is a pattern of ripples moving across them. Picture the entire cosmos as a still, dark sea with no shore. Most of it lies flat and silent, but here and there, ripples race across the surface, and where two ripples cross, they can join, split, or burst into new ripples. Those crossings and burstings are the whole story of matter. Stars, planets, your body, this very thought in your head, all of it is ripples meeting on the invisible sea. This is the true bottom floor of reality that we have been descending toward. Below the atom, below the proton, below the quark, there are no smaller marbles waiting. There are only fields, and they're trembling. But calling something an invisible ocean that fills all of space raises an obvious and dangerous question. If this field is truly everywhere, why can we not feel it? Why does empty space feel empty when it is supposedly packed with an ocean in every direction? The answer is that empty space is not empty, and what it hides is terrifying. If space is flooded with invisible fields in every direction, you should be swimming in them right now. So why does the air in front of your face feel like nothing? Why does the gap between the Earth and the Moon look like pure, cold emptiness? The answer is that a field can be present and still be quiet. Think of the ocean again on a dead calm night. The water is there, immense and heavy, stretching past the horizon. But if the surface is perfectly flat, with no waves at all, and you are floating in the dark, you might not even know the water exists until something disturbs it. The field of space is like that calm water. It fills everything. Yet when it lies flat, it makes no ripples, and no ripples means no particles, which to us looks like empty space. So, the emptiness you see is a field at rest. Poke it hard enough, feed energy into it, and the flat surface leaps up into a ripple, and that ripple is a brand new particle appearing out of what looked like nothing. This is exactly what the giant machines called particle colliders do. Deep underground, they take particles and slam them together at nearly the speed of light. The crash pours a huge burst of energy into one tiny point of space, and out of that point, new particles spray in all directions, particles that were not there a moment before. The colliders are not smashing marbles into smaller marbles. They are hitting the invisible ocean so hard that the calm surface erupts into a storm of fresh ripples. That is where new particles come from. Feed enough energy into a field, and the field answers by making a ripple, and the ripple is a particle born fresh from a patch of space that held nothing at all that you could ever have seen. Here is the piece that should stop your breath. The energy that becomes the new particle and the weight of that new particle are the same thing. A ripple with more energy is a heavier particle. This is the real meaning of the most famous equation ever written, the one that says energy and mass are two faces of one coin. Weight is a form of energy. Energy can be poured into a field to make weight. The wall between stuff and energy, the wall you have felt your whole life, does not exist down here, which finally cracks open the mystery of the missing proton weight. If energy can become weight, then a proton crammed with furious internal energy would weigh far more than its calm little quarks alone. The storm inside it would show up on the scale as heaviness. We will chase that storm soon. But first, a warning about the calm surface itself. We have been picturing the flat, resting field as truly still, like glass. And it turns out that perfect stillness is forbidden. The field can never fully rest, never lie completely flat, not even in the emptiest, coldest void between the galaxies. Something deep in the rules of the universe keeps it forever trembling. And that endless tremble means that empty space is the most crowded, most violent place there is. Here is a fact so ordinary sounding that its strangeness slips right past you. Every electron in the universe is exactly, perfectly, flawlessly identical to every other electron. Not similar, not close, identical. The electron making this word appear in your eye right now has precisely the same weight, precisely the same charge, precisely the same everything as an electron burning inside a star 10 billion trillion miles away, and as one that has existed since the first moments after the universe began. Take any two electrons, anywhere, from any time, and there is no test in existence that could tell them apart. Now think about how weird that is by comparing it to the everyday world. No two grains of sand are identical. No two marbles are perfectly the same. Make a factory that stamps out metal balls as carefully as humanly possible. Measure them fine enough, and you will always find tiny differences. A scratch here, a few more atoms there. Real objects are always a little unique, because they are built from separate pieces in separate places. So if electrons were tiny objects, tiny grains, stamped out across a universe 14 billion years old, they should carry differences. Little dents, slight variations, some heavier, some lighter, some worn smoother than others by their long histories. That is what separate objects do. They accumulate their own stories, and those stories leave marks. But electrons carry no marks at all. They do not. They are copies so perfect that perfection is not even the right word, because copies still have an original. And here there is no original, only endless, flawless sameness. The field idea explains this instantly and beautifully. There is only one electron field, one, a single invisible ocean spread through all of space, and every electron in existence is a ripple in that one same ocean. So of course they are identical. They are all the same kind of wave in the same body of water. Asking why two electrons are identical is like asking why two waves on the same pond are both made of water. There is nothing else they could be made of. There is only the one field, and every electron is a ripple of it. Picture a single, endless drumhead stretched across the whole universe. Tap it anywhere and you get a beat. Tap it a billion places at once and you get a billion beats. And every beat is the same drum speaking. The electrons are the beats. The drum is the field. That is why they match. This tells you something staggering about what you are. The electrons in your brain are not your private property. They are ripples in a field that stretches to the edge of everything, the same field rippling in distant stars and in the empty dark between galaxies. You are made of disturbances in an ocean shared by the entire universe. And this shared ocean has a rule we have not touched yet, a rule that will feel impossible. The field can never hold perfectly still. Try to freeze it, cool it to the coldest temperature allowed by nature, Drain out every last scrap of energy, and it will still shiver. It cannot stop, and that unstoppable shiver is about to reveal that the emptiest vacuum in the universe is secretly boiling. Take a field, one of these invisible oceans, and try to make it perfectly still. Drain away every bit of energy. Cool it down as far as the laws of physics allow, all the way to the coldest possible temperature, the point where all ordinary motion is supposed to freeze. You will fail. The field will still be trembling, and the reason why is one of the strangest rules in all of nature. The rule is called the uncertainty principle, and here is the plain version. Nature refuses to let anything be completely pinned down. You can never know both exactly where something is and exactly how it is moving at the same time, with perfect sharpness. Push one to be perfectly certain, and the other blurs out into fog. This is not a limit of our instruments. It is a rule baked into reality itself. Now aim that rule at a field trying to hold still. A perfectly frozen, perfectly flat field would be completely pinned down. Its position would be exact, and its motion would be exactly zero, both known perfectly, at once. And nature forbids that. So the field is not allowed to fully stop. It is forced to keep a low, restless jitter forever, a shiver it can never shake off, even at the coldest edge of existence. Picture a guitar string that can never be fully silenced. You damp it with your hand, you wait, you beg it to be still, and it keeps humming the faintest possible hum, because total silence is against the rules. Every field in the universe hums that forbidden hum. Physicists call it the trembling of the vacuum, the energy that is left over when every other scrap of energy is gone. Feel where this leads. Empty space, the truest emptiness there is, the void far from any star, is not calm and dead. It is quietly shaking in every direction, all the time, because the fields that fill it can never lie flat. The stillness of the night sky is a performance. Underneath, everything trembles. And this trembling is far more than a background hum you could ever ignore. It has real muscle. That leftover shiver carries genuine energy. And remember what energy can do to a field. Feed a field enough energy, and it leaps up into a ripple. And a ripple is a particle. So, a field that is forever trembling is forever on the edge of coughing up particles from nothing at all, always poised to spill matter into the void. Which is exactly what happens. The trembling vacuum is constantly, everywhere, sputtering tiny particles into brief existence and swallowing them back again, trillions of times faster than you could ever hope to catch a single one. The emptiest cubic inch of space between the galaxies is a churning froth of things flickering into being and vanishing, over and over, without pause, since the beginning of time. The void is the busiest place in the universe, and the particles it conjures from nothing are real, provably real. We can catch their effects. There is a force you can measure in a laboratory, a genuine push you can feel, that comes from these ghost particles boiling out of empty space. To understand that force, we first have to meet the ghosts. The trembling vacuum has a loophole, and it is the most audacious loophole in all of nature. Using it, empty space can create particles out of nothing at all, as long as it pays the debt back fast enough. The loophole comes straight from the uncertainty rule. Nature will not let energy be pinned down perfectly over a short stretch of time, and that fuzziness means a tiny amount of energy can appear from nowhere, out of pure emptiness, for a brief flicker, so long as it vanishes again almost instantly. The universe lets you borrow energy from nothing on one condition. You must pay it back before anyone can catch you holding it. So here is what happens in every patch of empty space, everywhere, always. A little energy gets borrowed from the void. That energy, being energy, leaps up in a field and becomes a pair of particles born together out of nothing. They exist for the shortest sliver of time imaginable. Then they crash back together, cancel out, and return the borrowed energy to the void. Debt paid, no trace left. Physicists call these fleeting things virtual particles. They are born from borrowed energy, live for an almost unimaginably tiny moment, and die before they can be directly seen. And this is a constant event, not a rare one. It is happening in staggering numbers in every corner of space, right now, in the room around you, in the space inside your own body, and in the deepest void beyond the farthest galaxy. There is nowhere it does not happen. Empty space seethes with these pairs, appearing and vanishing like foam on a boiling sea, endlessly, in numbers no one could ever count. Picture a still black pond at midnight. Watch closely, and the surface keeps popping with tiny bubbles that rise and burst before you can point at them. Blink, and they are gone, replaced by new ones. The pond looks calm from a distance, but up close, it never rests. That popping, foaming surface is what empty space is truly like at the smallest scale. The bubbles are the virtual particles, borrowed from nothing, paid back in an instant. Now, you might reasonably think this is a wild story physicists made up to amuse themselves. Particles that appear and vanish too fast to ever see, born from a loophole in a rule about fuzziness. It sounds invented. It sounds like a fairy tale dressed in mathematics, a convenient fiction with no way to ever test it. That is exactly what many people assumed at first. But nature gave us a way to check. If empty space is truly boiling with these ghost pairs, then it should be possible, with a clever enough setup, to change how much boiling happens in one spot and to feel the difference as a real, physical push. A force pressing on solid objects, created by the trembling of the void itself. That experiment has been done. The push is real. It has been measured, and it stands as some of the clearest proof we have that empty space is not empty, that the vacuum genuinely churns with particles flickering out of nothing. The next chapter is that experiment, a force squeezed straight out of emptiness, and it is one of the eeriest results in all of science. Take two flat metal plates, ordinary, smooth, uncharged, hang them in a vacuum, facing each other, and bring them extremely close together, closer than the width of a hair. Then let go and watch. The plates drift toward each other. They feel a gentle, real pull, as if the empty space between them were quietly sucking them together. No magnetism, no charge, no glue, nothing you can see connects them, yet the pull is there, and you can measure it. This is one of the strangest measured facts in physics, and the culprit is the boiling vacuum itself. Remember that empty space is packed with virtual particles flickering in and out, and that these come in waves of every possible size, from long, lazy ripples to short, frantic ones. Out in the open space around the plates, waves of all sizes are allowed. They churn freely in every direction, but squeeze into the narrow gap between the two close plates, and something changes. The gap is so tight that only certain wave sizes fit inside it. The big, long waves cannot squeeze in, they get shut out. So the space inside the gap has fewer kinds of ripples boiling in it than the space outside. Fewer waves inside means the vacuum inside is pushing outward, a little more weakly than the vacuum outside is pushing inward. The outside wins, and the two plates get shoved together by the sheer imbalance of empty space pressing on them. Let that picture settle. The plates are pushed together by nothing, by the difference between how much emptiness boils outside them versus between them. It is a force built entirely from the churning of the void, and it is strong enough to move real metal you could hold in your hand. Here is a way to feel it. Imagine two ships floating side by side on a choppy sea, close together. The big rolling waves of the open ocean cannot fit into the narrow channel between the hulls, so the water between the ships is calmer than the water outside. The wild waves outside push the ships inward harder than the calm water between them pushes back, and the two ships get nudged toward each other by the sea itself. The plates are the ships, the boiling vacuum is the sea, and the emptiness does the pushing. This experiment has been done for real, many times, with ever greater care. The pull matches the prediction, which means the story we told was true all along. Empty space genuinely churns with countless particles flickering out of nothing, and that churning is powerful enough to press two metal plates together across a gap of pure vacuum. So, the deepest emptiness in the universe is alive with energy and motion, a restless froth that can push on solid metal you could hold in your hand. And if nearly empty space is already this crowded and this energetic, imagine the inside of a proton, where the fields are screaming at full volume with the strongest force in all of nature, packed and roaring in a space too small to picture. That is where our missing weight has been hiding this whole time. It is time to open the proton and look directly into the storm. We left a mystery unsolved. A proton weighs about 100 times more than its 3 quarks added together, and the missing 99% seem to come from nowhere. Now we have the tools to find it. And the answer is that the inside of a proton is not a quiet box holding 3 still marbles. It is a furnace. Start with the size. A proton is unimaginably tiny. You could line up around 100 billion of them across the width of a single human hair. And crammed into that unthinkably small space is a fury of activity happening at nearly the speed of light. The proton is a roaring, churning, boiling interior, closer to the heart of a raging fire than to a bag of object. The 3 quarks are still in there, but they are not sitting still. They are trapped inside that microscopic space, and trapping a particle in a tiny box forces it to move. This is the same uncertainty rule from before. Pin a particle into a very small place, and you cannot pin down its motion, so it is forced to race around, faster and faster the smaller the box gets. And the proton is one of the tiniest boxes in nature. So the quarks tear around inside at speeds close to the speed of light, carrying enormous energy of motion. And that racing motion is only part of the storm. The interior also swarms with countless extra particles flickering in and out, the same ghostly pairs we met in the vacuum. But here they are supercharged, because the field inside a proton is not calm. It is the most violent field in nature, the strong force, screaming at full volume. The proton is packed with this seething, ever-changing crowd of appearing and vanishing particles layered on top of the 3 racing quarks. So the true picture of a proton is a tiny cauldron holding a permanent storm, racing quarks, swarming ghost pairs, and the raging field that binds them, crackling with energy in every direction, all of it locked inside a space too small to imagine. Now remember the equation that ties energy to weight. Energy has weight, and this storm is nothing but energy. The energy of the racing quarks, the energy of the swarming pairs, the energy of the screaming field. Pile all that energy together, ask the universe what it weighs, and the answer is the weight of the proton. The missing 99% was never a hidden object. It was the weight of the storm. Picture a sealed glass jar that looks empty but holds a tiny, perfect hurricane, spinning at unthinkable speed. Weigh the jar and it is heavy, far heavier than the few specks of dust caught in the wind. The weight is in the fury of the storm, not in the dust. The proton is that jar. The quarks are the dust. And the hurricane is where your body weight actually lives. This is the answer to where matter gets its heft. Solid stuff is mostly trapped energy wearing the mask of weight. But this raises a deeper question. The 3 quarks do have a small weight of their own, that tiny 1%. Where does even that come from? The answer is a second invisible field, one that switched on in the first instant of the universe and gave the quarks the only real weight they own. We solved the big mystery. Almost all of a proton's weight is trapped energy, the weight of the storm inside. But a sliver remains. The quarks themselves carry a tiny weight of their own, that leftover 1%, and an electron, which has no storm inside it, has a small weight too. So where does the weight of the truly fundamental particles come from? The ripples that have no smaller parts? The answer is another field, a special one, unlike any we have met, and it fills all of space with an invisible presence that gives the basic particles their heft. Scientists call it the Higgs field, after one of the people who dreamed it up. Here is what makes it strange. Every other field we have discussed sits calm and flat when nothing disturbs it, resting at zero, silent until a ripple comes along. The Higgs field is different. It does not rest at zero. Everywhere in the universe, in every corner of space, this field holds a steady non-zero value, always switched on, always present, like a faint glow soaked into the fabric of reality that never fades. And as the fundamental particles move through this ever-present field, it clings to them. It resists their motion. It makes them harder to push around. And that resistance to being pushed is exactly what weight is. Weight is nothing more than how strongly something resists a shove. So a particle that grips the Higgs field strongly feels heavy, and a particle that barely grips it feels light. This is why different particles have different weights. It is all about how tightly each one holds onto the Higgs field as it moves. A particle that interacts strongly gets dragged hard and comes out heavy. A particle that interacts weakly slips through almost freely and comes out light. The field is the same everywhere. The difference is how much each particle feels it. There is a famous way to picture this, though we will fix a flaw in it soon. Imagine a crowded room full of people, spread evenly everywhere. A very popular celebrity tries to cross the room, and the crowd clusters around them, slowing every step, making them hard to get moving and hard to stop. That clustering, that drag, is like weight. Meanwhile, a stranger nobody recognizes walks straight across, barely slowed at all. The celebrity is the heavy particle, the stranger is the light one, the crowd is the Higgs field, filling the whole room. This field was not always switched on. In the first tiny fraction of a second after the universe began, everything was so blisteringly hot that the Higgs field lay flat like all the others, and the fundamental particles had no weight at all. They flew about at the speed of light, weightless and free. Then the universe cooled, and at one precise moment, the Higgs field switched on across all of space at once, and in that instant, the fundamental particles gained the weight they have carried ever since. The idea was so bold that people doubted it for decades. To believe it, physicists needed to catch the field in the act, and the only way to prove a field is real is to make it ripple, to strike it hard enough to produce its particle. Hunting that single ripple became one of the greatest chases in the history of science. To prove the Higgs field is real, you have to make it ripple. And making it ripple means hitting it so hard that the field jumps up and produces its own particle, a single bump in the ever-present glow, called the Higgs boson. Find that particle, and you have proven the field exists. Fail to find it, and the whole beautiful idea might be a fantasy. There was a problem. The Higgs ripple is extraordinarily heavy, far heavier than most particles. And remember that heavy particles take enormous energy to create. To slam the Higgs field hard enough to cough one up, you would need to pour in a staggering burst of energy, concentrated into a spot smaller than an atom. No ordinary machine could do it, so the world built the largest machine in human history to try. Near Geneva, buried underground, engineers dug a circular tunnel 17 miles around, big enough that a full loop is longer than many city marathons. Inside it, they sent beams of protons racing in opposite directions, whipping around the ring millions of times a second, faster and faster, until they were moving at very nearly the speed of light. Then they steered the beams to crash head-on. Each collision packed an unthinkable amount of energy into a single microscopic point, striking the fields of nature like a hammer blow. Most crashes just made ordinary sprays of familiar particles, but every so often, buried in trillions of collisions, the hammer might strike the Higgs field hard enough to make it ripple, and for the tiniest sliver of time, a real Higgs particle would flash into being. There was a catch that made the hunt agonizing. The Higgs particle does not stick around. The instant it appears, it falls apart into a shower of other, more ordinary particles, and vanishes. So, no one could ever see it directly. Scientists had to work backward, like detectives at a crime scene, sifting through the debris of countless collisions, hunting for the exact pattern of leftover particles that only a dying Higgs would leave behind. They collided protons for years. They gathered mountains of data, more than any human could ever read, and two enormous teams, working separately so they could check each other, combed through it, looking for the fingerprint. In the summer of the year 2012, both teams stood up and announced the same thing. Hidden in the wreckage of all those collisions was the unmistakable signature of a new particle, with exactly the weight the Higgs was predicted to have. After nearly 50 years of searching, they had caught the ripple. The field was real. Think about the size of that moment. A single idea, dreamed up with pencil and paper, that empty space is soaked in an invisible field, giving particles their weight, had been confirmed by building the biggest machine ever made and smashing matter together a quadrillion times. The universe answered, the field is there. But the popular story told to the public, the crowded room slowing the celebrity, hides a beautiful lie. The Higgs field does not give particles weight by slowing them down like thick syrup. What it truly does is far stranger and more musical, and understanding it means seeing every particle in the universe as a kind of humming string. The story you usually hear about the Higgs field is that it works like syrup or molasses, slowing particles down as they wade through it, and that drag is their weight. It is a helpful picture. It is also wrong in a deep way, and the truth underneath is far more beautiful. Weight is really about vibration. Go back to the idea that every particle is a ripple in a field. Now sharpen that image. A particle sitting still is like a plucked guitar string, vibrating in place, humming at a certain rate. Every kind of particle has its own natural rate of humming, its own pitch, built into the field it belongs to. And here is the secret the universe has been keeping. The faster a particle hums as it sits there, the heavier it is. Weight is the pitch of a particle's vibration. A high, fast hum means heavy. A slow hum means light. Now bring in the Higgs field. Without it, the fundamental particles would have no hum at all. They would be silent. And a silent particle is a weightless one, doomed to fly at the speed of light forever, never able to sit still. The Higgs field, switched on everywhere, is what lets these particles vibrate in place. It grabs them and gives them a pitch. It tunes them, the way tightening a string sets the note it will sing. So the Higgs field is not molasses dragging particles down. It is a cosmic tuning system, setting the pitch at which every fundamental particle hums. A particle that responds strongly to the field gets tuned to a high, fast hum and comes out heavy. A particle that barely responds gets a low, slow hum and comes out light. Change how strongly a particle feels the field, and you change its pitch, and you change its weight. Picture a vast church organ with countless pipes, and every pipe is a different kind of particle. Blow air through them, and each sounds its own note. The deep, slow notes are the light particles. The high, fast notes are the heavy ones. And the Higgs field is the air pressure filling the whole organ, the thing that lets any pipe make a sound at all. Cut off that pressure, and the organ falls silent, every particle weightless, the music of matter gone. This is a far stranger and lovelier truth than syrup. The weight of everything, the heft of your own body, is not stuff being slowed by cosmic mud. It is a chord. Every fundamental particle in you is a tiny standing vibration, humming at its own pitch, tuned by a field that switched on in the universe's first instant. You are, at the deepest level, a piece of music the cosmos has been playing for 14 billion years. And this musical picture explains a mystery that has been sitting quietly in the background this whole time. There is one particle that refuses to hum at all. It has no pitch, no weight, and it can never, ever sit still. It is the most familiar thing in the universe, streaming into your eyes at this very moment. It is light, and its weightlessness is the key to why the cosmos looks the way it does. There is one particle that plays no part in the game of weight at all. It ignores the Higgs field completely. It has no hum, no pitch, no heft whatsoever, and you are soaked in it right now. It is light, and its particles are called photons, the little packets of energy that carry every color you have ever seen. A photon weighs exactly nothing, not almost nothing, precisely, perfectly zero. This is why light behaves so unlike everything else in the universe. Every particle that carries weight is stuck below a cosmic speed limit, the speed of light, and can never quite reach it, because pushing a weighty thing faster and faster takes more and more energy the closer it gets, and reaching that top speed would take an infinite amount. So massive particles are forever locked just below the limit. But a photon, carrying no weight at all, faces no such barrier. It does not build up on its way to the top speed. It is simply born already moving at the fastest speed the universe allows, and it travels at that speed forever, from the instant it appears to the instant it is absorbed. Light does not accelerate. It does not speed up from rest. The moment a photon exists, it is already going at full cosmic speed, and it never slows, never rests, never stops, unless something swallows it whole. And because a photon never experiences rest, it never sits still to hum, which is exactly why it has no weight. Remember, weight is the pitch of a particle humming in place. A photon can never be in place. It is pure motion, always racing, so it has no pitch to hum, and therefore nothing for the Higgs field to grab. Light and weight are strangers. They have never met. Here is a comparison to feel it. Imagine a bell that only makes sound while it is standing still on a table, humming after you strike it. Now imagine a gust of wind that only exists while rushing forward and dies the instant it stops. The bell is a particle with weight, humming in place. The photon is the wind, alive only in motion, silent and weightless because it can never hold still to ring. This tiny fact, that light has no weight, shapes the entire universe you see. Because photons travel at the top speed and never tire, the light from unimaginably distant stars can cross the cosmos for billions of years and still reach your eye. When you look up at the night sky, you are catching weightless photons that have been racing toward you since before the Earth existed, ancient messengers that have not aged a single moment on their journey, because for something moving at the speed of light, in a strange sense, no time passes at all. So the universe is knitted together by a weightless particle that lives only to run, and the story of what has weight and what does not, of humming strings and silent light, all came from one bold idea, that particles are ripples in fields. But that same idea, when a brilliant and stubborn man first followed it to its logical end, spat out an answer so monstrous that he almost refused to believe it. His equation demanded that a shadow universe of mirror matter must exist, and it was right. In the late 1920s, a quiet, intensely logical young Englishman named Paul Dirac set himself a problem that had stumped everyone. He wanted a single equation that described the electron correctly, one that obeyed both the rules of the very small and the rules of the very fast at the same time. Nobody had managed to fit those two great theories together for a particle like the electron. Dirac, working mostly in silence and trusting the mathematics above all else, found the equation. It was gorgeous. It described the electron perfectly. It even explained features of the electron that had been mysteries before, falling out of the math like gifts. By every measure, it was a triumph. But the equation had a passenger nobody ordered. When Dirac solved it fully, it did not describe only the ordinary electron. It insisted, with cold mathematical certainty, that another kind of particle must also exist. A particle with the same weight as the electron, but with the opposite electric charge. A mirror image electron. A twin made of what we would come to call antimatter. This was deeply unwelcome. No such particle had ever been seen anywhere, in any experiment, by anyone. Ordinary matter was made of familiar pieces, and here was an equation demanding a whole shadow version of the electron, a thing with a backward charge, haunting the mathematics and refusing to go away. Many scientists assumed it was simply a mistake, a flaw hidden in the theory, an ugly phantom that better work would eventually explain away and erase. Dirac himself was uneasy, but he trusted the equation more than he trusted common sense. He reasoned that if the mathematics was this beautiful and this correct everywhere else, then it deserved to be believed even where it sounded absurd. So he made one of the boldest bets in the history of science. He predicted that this mirror particle was real, that somewhere out in the universe there existed antimatter, opposite twins of the ordinary particles we knew, waiting to be found. Picture a master locksmith who builds a lock so perfect that its design forces a matching key to exist, a key he has never seen and no one has ever held. The design is so exact that the key must be real, or the whole thing is nonsense. Dirac's equation was that lock. The mirror electron was the key it demanded, and he chose to believe the design. For a few years, the prediction hung in the air, unproven, doubted, a strange consequence of a strange equation. Some of the greatest physicists alive thought it was a mathematical accident. Dirac waited. Then, in a completely separate experiment, a young scientist studying the faint rain of particles that falls on Earth from deep space noticed something in his detector that made no sense, a track curving the wrong way. A particle that looked exactly like an electron in every respect, except that it bent as though its charge were backward. He was not even looking for Dirac's shadow twin, and had never expected to see one, but he had just photographed it, and it would confirm that our universe has an opposite, one that annihilates ordinary matter on contact in a flash of pure energy. In the year 1932, a young American named Carl Anderson was studying cosmic rays, the constant sleet of particles that pours onto our planet from the depths of space. To catch them, he used a chamber filled with vapor, rigged so that any charged particle streaking through would leave a thin trail, like the white line a jet leaves across the sky. He wrapped the whole thing in a magnet, because a magnet bends the path of a charged particle, and the direction it bends reveals whether the charge is positive or negative. Track after track curved the way an ordinary electron should, bending in the direction that a negative charge must bend. Routine. Expected. Then one photograph stopped him cold. There was a track that looked, in every single detail, exactly like an electron. Same weight, same behavior, same everything, except it curved the opposite way. It bent as though its charge were backward, as though it were an electron turned inside out. Anderson had photographed a particle with the weight of an electron and the opposite charge. Dirac's impossible mirror twin, the shadow demanded by the equation, sitting right there in a photograph. The antimatter partner of the electron was real. It even earned a name of its own, marking it as the positive version of the electron. The bet had paid off. A young man following pure mathematics had predicted an entire hidden category of matter, sight unseen, and another young man, not even hunting for it, had caught it falling from the sky. This is one of the most stunning triumphs of the human mind, a case where the universe was forced to confess a secret because an equation said it must be there. Once scientists knew to look, antimatter turned up everywhere. Every kind of particle, it turned out, has an antimatter twin, an opposite version with reverse charge and the same weight. The proton has one. Even particles deep inside the atom have theirs. The shadow world was not a single strange electron. It was a complete mirror of all ordinary matter, a full anti-version of everything. Picture a photograph of a person and the exact negative of that photograph, where every light is dark and every dark is light, yet the shape is perfectly the same. Ordinary matter is the photograph. Antimatter is the negative. Same form, reversed in the deepest way, and these twins carry a terrible secret. When a particle of matter meets its antimatter twin, they do not bounce and they do not merge. They destroy each other utterly, both vanishing in the same instant, their entire being converted into a burst of pure energy, usually a flash of light. Matter and antimatter cannot coexist. To touch your opposite is to end completely for both of you. We can make antimatter today, in tiny amounts, in the great colliders. We can even trap a few particles of it for a while, held in magnetic cages so it never touches the walls, because touching ordinary matter would annihilate it instantly. But this raises a haunting puzzle that reaches back to the birth of the universe. If matter and antimatter are perfect twins, born together and destroying each other on contact, then why is there any matter left at all? Here is a question that should keep you up at night. If every particle of matter has a perfect antimatter twin, and the two annihilate each other completely on contact, then why is there a universe? Why is there anything instead of nothing? Follow the logic back to the beginning. In the searing chaos just after the universe began, energy was pouring into the fields of nature, coughing up particles everywhere. But there is a rule about how this creation works. When pure energy turns into matter, it makes matter and antimatter in equal pairs, one twin and one anti-twin born together, always balanced. A particle here, its opposite there, in matched numbers, so the early universe should have made exactly as much antimatter as matter, perfectly equal. And then, as everything cooled and the particles began to meet, every particle of matter should have found its antimatter twin and annihilated with it, both vanishing into a flash of light. Matter and antimatter, born in equal amounts, wiping each other out completely. If that had happened, the universe would be a vast, cold, empty ocean of light and nothing else. No stars, no planets, no atoms, no you, just a sea of leftover radiation drifting through endless dark, with not a single scrap of solid matter anywhere, because every last particle would have found its opposite and been destroyed. But that is not the universe we live in. You are here. Stars burn, galaxies spin, matter clearly won. Somehow, when all the annihilating was done, a little bit of matter was left over, unmatched, with no antimatter twin to destroy it. And everything you have ever seen or touched is built from that tiny surviving remainder. How tiny? For roughly every billion twins of matter and antimatter that annihilated in the young universe, it seems there was just one extra particle of matter with no partner. 1 in a billion. That microscopic imbalance, that single leftover out of a billion, is the entire material world. Every star, every planet, every living thing is made from the crumbs that were left when the great annihilation ran out of partners. Picture two vast armies, matter and antimatter, marching toward each other across a plain, each soldier pairing off with an enemy and both vanishing in a burst of light. When the dust clears, the whole field is empty, except for a handful of soldiers on one side who found no one to fight. Those few leftover soldiers are all the matter in the universe. We are the survivors of a war that annihilated almost everyone. Why was there that one extra particle in a billion? Why did nature tilt ever so slightly toward matter instead of a perfect, deadly balance? This is one of the great unsolved mysteries of physics. Scientists have found tiny hints that matter and antimatter are not perfect mirror twins. After all, that the universe cheats just a little in favor of matter. But the full answer is still out there, waiting. So, your existence traces back to a faint imperfection in the birth of the cosmos, and matter itself, this leftover survivor, has properties even stranger than its origin. Because every one of these particles carries a hidden quality that behaves like spinning, yet nothing is actually turning. It is the weirdest trait matter has, and it decides whether you can walk through a wall. Every particle of matter carries a strange, hidden property, and physicists gave it a misleading name. They call it spin. The name makes you picture a tiny ball twirling like a top, turning on an axis. Throw that picture away right now, because nothing is actually spinning, and yet the property is real, measurable, and absolutely central to why the world holds together. When scientists first found this trait, it acted a lot like the spinning of a top. A particle behaved as though it were rotating, carrying the same kind of quality a spinning object has, and it responded to magnets in a way that fit the idea of a whirling charge. So the name spin stuck. But when they looked harder, the picture fell apart in impossible ways. For one thing, a particle like an electron has no size to speak of. as far as anyone can measure. It is a point, and a point cannot rotate, because there is nothing off-center to go around. For another, if the electron truly were a tiny ball, spinning fast enough to explain its behavior, the surface would have to move faster than the speed of light, which nature forbids. So the electron is not a spinning ball. It cannot be. Yet it carries this spin quality anyway, as surely as it carries its charge and its weight. Spin, it turns out, is a built-in feature of a particle, as basic as its weight. It is a fixed amount of a certain kind of rotational quality that the particle simply has, woven into what it is, without anything physically turning. It is one of nature's clearest signs that particles are not tiny objects at all. A real object either spins or it does not. This is a spin with no spinning, a rotation with nothing that rotates, and it makes sense only when you accept that a particle is a ripple in a field, obeying rules that have no match in the world of everyday things. Picture the hands of a clock that show a definite time, pointing in a definite direction, giving you real information you can use, on a clock face that has no gears inside and never actually ticks. The reading is real, the mechanism is absent. Spin is like that reading, a real, usable quality with no turning machinery behind it. Now here is why this strange trait matters more than almost anything else. The exact amount of spin a particle carries sorts all the matter and energy in the universe into two great families. Some particles carry a spin that comes in a certain kind of amount, and some carry a different kind, and these two families follow opposite rules for how they share space with their own kind. One family is willing to pile together without limit. The other family absolutely refuses to share the same state, ever, under any circumstances. That single difference, born from the invisible, motionless spin, decides the entire structure of the world. It is why stars can collapse, why atoms have their shapes, and why your hand does not sink through the table when you rest it down. To see how a rule about spin builds the solid world, we have to meet the two families and the fierce law that keeps one of them apart. The invisible spin splits all particles into two great families, and the difference between them builds the structure of everything you know. One family is made of the particles that carry force, the messengers of nature, and light belongs to this family. These particles are generous with space. You can pile any number of them into the same state, stacked on top of one another without limit, all doing the exact same thing in the exact same place. This is why you can make a laser, a beam where countless particles of light march in perfect lockstep, identical, all crammed into the same state. The force carriers love to gather. The other family is made of the particles that build matter, the quarks and electrons that make up you, the ground, the stars, and these particles follow the opposite rule, a rule so strict it shapes the whole material universe. Two of them can never, ever occupy the same state at the same time. No matter how hard you push, no matter how much you squeeze, two of these matter particles refuse to share the same place in the same way. Each one demands its own spot. This iron law is called the exclusion principle, and it is one of the most important rules in all of nature. Follow what it builds. Inside an atom, the electrons must arrange themselves around the center, and because no two can share the same state, they are forced to stack up in layers, in shells, each electron taking a spot no other can have. That forced stacking gives every kind of atom its structure, and that structure is the entire reason chemistry exists. The way atoms bond, the way molecules form, all of it flows from electrons being forbidden to crowd together. Without this rule, every atom would collapse into a featureless lump, and there would be no chemistry, no life. And here is the part you can feel with your own hand. When you press your palm against a table, the electrons in your skin come close to the electrons in the wood, but they cannot merge into the same state, because the exclusion rule forbids it. So they push back, hard, refusing to share space. That refusal is the resistance you feel. That is the solidness of the table. Remember from the very beginning that atoms are almost entirely empty. Your hand and the table are both mostly hollow space. By raw size, your hand should pass through the table like a ghost through fog. It stops for one reason only. The electrons in it are forbidden from sharing states with the electrons in the table, and so they shove each other away. The floor holds you up because of a rule about spin, a law reaching up through the emptiness to keep you standing. Picture a vast parking lot with countless numbered spaces, where the law says no two cars may ever park in the same numbered spot. Every car must find its own. That single rule forces the whole lot into an ordered structure and keeps the cars from ever collapsing into one pile. The matter particles obey that law absolutely, and it is why the world has shape and firmness instead of dissolving into mush. So solidity itself is a quantum rule in disguise, and that is only the beginning of how bizarre these particles behave, because a single one of them can do something no object ever could. It can be in two places at once. A single particle can be in two places at the same time. This is not a trick of loose language. It is a literal description of how matter behaves at the deepest level, and it has been confirmed in experiment after experiment for a century. A particle, left alone and unwatched, does not sit at one location. It spreads into a haze of every place it could possibly be, all at once. Go back to the lonely electron passing through two slits, building up a wave pattern one dot at a time. The only way to explain it is that each single electron went through both slits at once, as a spread-out wave, and rippled against itself before landing. It did not secretly go through one slit or the other. It genuinely took both paths together. A particle exploring every route at the same time is called being in a superposition, and it is the normal state of matter when nothing is looking. Picture the particle before you measure it as a spread-out cloud of possibility, thickest where it is most likely to be found, and thin where it is unlikely, but present in many places at once, all of them real, all at the same time. The particle is not hiding at one secret spot inside the cloud. The cloud is the particle. It is smeared across many places, many speeds, many possibilities, existing in all of them together. This is why the small world feels so alien. In everyday life, a ball is either here or there. A coin lands heads or tails. But a particle, before you check on it, is genuinely all its options at once, layered over each other like many faint photographs printed on the same page. Every possible outcome is present, coexisting, until the moment something interferes. Here is a comparison to hold on to. Think of a struck bell, humming not one note but a rich blend of many tones at the same time, all sounding together in a single complex chord. You cannot point to one note and say that is the only one the bell is playing. The bell is playing all of them at once, and the sound is the whole blend. A particle is like that chord, existing as a blend of all its possible states, not one, until something forces it to choose. And there is the strangest part, hiding in that word choose. The particle stays spread across all its possibilities, only while nothing measures it. The instant you actually look, the instant anything interacts with it to pin down where it is, the haze collapses. All those coexisting possibilities snap down to a single, definite answer. The spread-out cloud vanishes, and the particle is suddenly, sharply, in one place, as if it had been there all along. This means the simple act of measuring changes reality itself. Looking is not a passive thing at the quantum scale. To look is to force the universe to pick. Before the measurement, many futures coexist. After it, only one remains, and the rest are gone. And this raises one of the most disturbing questions in all of science. What exactly counts as looking? What is powerful enough to force a spread-out particle to collapse into a single fate? We reached a bizarre conclusion. A particle stays smeared across many possibilities until something measures it, and then it snaps to a single answer, so everything hangs on one question. What counts as a measurement? What is it about looking that forces the universe to choose? Start with what we know for certain. As long as a particle is truly left alone, sealed off from everything. It stays in its spread-out haze of many possibilities at once. The trouble begins the moment it touches the rest of the world. Bounce a single speck of light off it to see where it is, and that touch is enough. The haze collapses. The particle picks one spot. The very act of gathering information about the particle forces it to commit. And this is the heart of the weirdness. At the quantum scale, you cannot look at something without touching it, and you cannot touch it without changing it. To find out where a particle is, you must interact with it, and that interaction is what shatters its cloud of possibilities into a single fact. There is no gentle, invisible way to peek. Looking is always a shove. Picture trying to find a floating soap bubble in a pitch-black room by feeling around with your hands. The only way to locate it is to touch it, and the instant you touch it, it pops. You can know exactly where it was, but only by destroying the very state you were trying to observe. The quantum world is like that dark room. Every measurement pops the bubble of possibilities and leaves behind a single definite outcome. For a long time, this led people to wonder something eerie. Does it take a conscious mind, an actual observer, to collapse the haze? Is human awareness somehow special, reaching into the quantum world and forcing it to decide? It is a seductive idea, and it has fooled many people. But the truth is more grounded. It does not take a mind. It takes an interaction. Any interaction, with anything at all, that carries away information about the particle will do it. A stray photon, a bump from an air molecule, a touch from any part of the wider world. The reason big, everyday objects never seem to be in two places at once now becomes clear. A large object, a ball, a chair, you, is made of countless particles, constantly touching the world around them, drenched in light and air and heat. Every one of those touches is a measurement. So a big object is being measured billions of times over, from every direction, and it can never hold onto a spread-out haze for even the tiniest instant, which is why your chair is always in exactly one place. The strangeness of the quantum world does not disappear as things get bigger. It gets drowned out, hidden under a storm of constant measurement. The two places at once behavior is still down there in every particle of you, but the endless bumping of the world keeps forcing it into a single, ordinary reality, moment by moment. Yet even this is not the strangest thing particles can do, because two particles can become linked in a way that ties their fates together across any distance, so that measuring one instantly decides the other, even if they sit on opposite sides of the galaxy. It troubled the greatest scientist of the age so deeply that he called it spooky, and spent years trying to prove it could not be real. Two particles can be joined in a way that welds their fates together, so tightly that measuring one instantly settles the other, no matter how far apart they are. Put one on Earth and carry the other to the far side of the galaxy, and the link holds. Measure the one here, and in that same instant, the one across the galaxy is decided. This connection is called entanglement, and it is real, tested, and confirmed beyond doubt. Here is how it works. Under the right conditions, two particles can be created together in a shared state, so that certain of their properties are linked. Neither one has a definite answer of its own yet. Both hang in the spread-out haze of possibility we have been describing. But the haze is shared. Their fates are woven together. Whatever one turns out to be, the other must match, in a fixed way set the moment they were joined. Now separate them. Send them light years apart. As long as neither is measured, both remain in their blur of possibilities, waiting. Then you measure one. It snaps to a definite answer, and in that very instant, the other particle, however far away, snaps to its matching answer too, at once, with no wait for any signal to cross the gap. The far particle knew what to become the moment its partner was measured, across any distance, with nothing passing between them that we can find. This drove Albert Einstein to distraction. He had shown that nothing can travel faster than light, and here was a connection that seemed to act instantly across any gap. He refused to accept it, calling it spooky action at a distance, and he argued for years that the particles must secretly carry hidden instructions from the start, a prearranged plan. It only looks spooky, he insisted, because we could not see the plan. For decades, it was a philosophical argument with no way to settle it. Then someone figured out a clever test, a specific pattern of measurements that would come out one way if Einstein was right and the particles carried hidden plans, and a different way if the spooky link was real. Scientists ran the test again and again in ever more careful and airtight forms. Einstein was wrong. The particles carry no hidden plan. The link is genuine. The universe truly does tie the fates of entangled particles together across any distance, instantly, in a way that has no explanation in terms of anything traveling between them. Picture a pair of magic coins minted together, sealed in boxes, and carried to opposite ends of the earth. Each box, unopened, holds a coin that is genuinely both heads and tails at once. Open one box and find heads, and in that instant, the coin in the far box becomes tails, guaranteed, though no message could have raced between them in time. The universe decides both the moment you look at one. There is a strict limit that keeps this from breaking the laws of nature, because the outcome of each measurement is random, so you cannot use the link to send a message faster than light. But the connection itself is undeniably real, and it hints that the deepest layer of reality is stitched together in ways that ignore distance entirely. To see how deep that stitching goes, we have to look at what happens when particles push and pull on each other, because even the forces between them turn out to be particles in disguise. When a magnet pulls a nail across a table, something reaches across the empty gap between them and tugs. For centuries, this was a genuine mystery. How can one object push or pull another without touching it across a stretch of nothing? The quantum answer is stranger and more wonderful than anyone expected. The forces of nature are carried by particles, thrown back and forth like messages between bits of matter. Every push and pull you have ever felt is really an exchange of tiny particles. When two electrons repel each other, they are tossing particles of light back and forth, and the throwing and catching is what shoves them apart. The force is not a mysterious influence stretching across the gap. It is a hail of messenger particles flying between the two, each one carrying a little push. Matter interacts by trading these messengers, and the trading is the force. Different forces have different messengers. The force that lights the world and binds atoms together, the electric and magnetic force, is carried by particles of light. The strong force deep inside the proton has its own messenger. Each force in nature works by flinging its own kind of particle between pieces of matter, and the character of the messenger sets the character of the force. Picture two people standing on frozen ponds, on slick ice, throwing a heavy ball back and forth between them. Each time one throws the ball, the throw shoves them backward, sliding them away. Each time the other catches it, the catch pushes them back too. From a distance, with the ball too small to see, it looks as though some invisible force is pushing the two apart, when really they are just trading a ball. That is how a pushing force works at the deepest level. Matter trades messengers, and the trade does the pushing. These messengers include the ghostly virtual particles we met earlier, borrowed briefly from the vacuum. When two particles interact through a force, they exchange a storm of these fleeting messengers, flickering into being just long enough to carry the push or pull, then vanishing. The empty space between two magnets is not empty at all. It is thick with borrowed messenger particles racing across, weaving the force out of the trembling vacuum itself. So the entire idea of a force reaching across empty space dissolves into something more concrete. Nothing reaches across nothing. Instead, matter is constantly throwing and catching a blizzard of tiny particles, and what we call a force, gravity aside, is the sum of all that throwing and catching. Even the pull of a magnet on your refrigerator is a swarm of invisible messengers traded faster than thought, shoving and tugging in a way that adds up to the steady pull you feel. This picture unites the whole quantum world. Matter is made of ripples in fields. Forces are made of ripples in fields too, thrown between the matter. Everything, the stuff and the forces that move it, is one grand dance of ripples on the invisible oceans that fill all of space. And among these forces, one stands apart in its ferocity. The messenger of the strong force, the one that binds quarks inside the proton, breaks a rule that all the other forces obey. It feels its own pull. It acts on itself. And that single strange fact is the reason a quark can never, ever escape. And the reason the storm inside the proton rages without end. The strong force is the most powerful force in nature, the one that binds quarks together inside every proton and neutron. And it obeys a rule that sets it apart from every other force, a rule that makes it monstrously, unbreakably strong. The messengers of the strong force feel the strong force themselves. They pull on each other. To see why this is so strange, compare it to the force of light. When two charged particles trade messengers of light to push each other, the messengers themselves are neutral. They carry the force, but they do not feel it. A particle of light does not pull on another particle of light. So the messengers fly straight between the charges, minding their own business, and the force weakens as the particles move apart, fading with distance the way the light of a candle fades as you walk away. The strong force does not behave this way at all. Its messengers, called gluons, carry the very quality that the strong force acts upon. So the gluons pull on each other. The messengers of the force are themselves gripped by the force. And this changes everything about how the force behaves across distance. Because the messengers attract one another, the strong force does not spread out and fade as quarks move apart. Instead, the messengers being flung between two quarks pull themselves together into a tight, narrow tube, a concentrated thread of force stretching directly from one quark to the other. And a tube like this does not weaken with distance. It behaves like a stretched elastic band. The farther you pull the two quarks apart, the more the band stretches, and the harder it pulls back. The force does not fade with distance. It grows. Picture two people holding the ends of a strong rubber band. When they stand close, the band is loose, and they can move freely. But as they walk apart, the band stretches tighter and tighter, yanking them back with growing strength. The strong force between two quarks is that rubber band. Nearby, the quarks feel almost free. Pull them apart, and the pull between them only rises, refusing to let go. This is why a lone quark has never been seen and never will be. Try to rip a single quark out of a proton, and the force between it and its neighbors climbs higher and higher as you pull, like stretching that band toward its breaking point. You pour more and more energy into the stretch, and then something extraordinary happens, something that seals the quark's imprisonment forever. The rubber band, stretched too far, does not simply snap and let the quark go free. It does something far stranger, using the very energy you fed into it to slam the door shut. The quarks are trapped for life, held by a force that only tightens its grip the more you fight it. Every other force in nature grows gentle as things move apart, releasing its hold with distance. The strong force does the reverse, growing fiercer the harder you pull, a jailer that clamps down tighter with every inch of escape. This lifelong imprisonment even has a name, and understanding what happens at the breaking point reveals where new matter itself comes from. Try to tear a single quark out of a proton. The strong force between it and its neighbors behaves like a stretching rubber band, pulling back harder the farther you drag it. So you pull, and you pour energy into the stretch, and the tension climbs. In your mind, you expect that if you just pull hard enough, the band will snap and the lone quark will fly free at last. That is not what happens. And what does happen is one of the most beautiful facts in all of physics. Remember that energy and matter are two faces of the same coin, and that pouring energy into a field can make new particles. As you stretch the band of strong force between the quarks, you are cramming more and more energy into that thin tube of force. The tension rises. The energy in the tube climbs higher and higher, and at a certain point, the tube holds so much energy that the universe finds it easier to do something remarkable. Rather than let the band stretch any further, the energy in the tube suddenly converts into a brand new pair of particles, a fresh quark and a fresh antiquark, born right there in the middle of the stretch. So the band does not snap into two loose ends with a free quark on one side. Instead, at the moment of breaking, two new particles appear out of the stored energy, and they instantly attach to the broken ends. The result is that you now have two proper pairs, each with its quark and its partner held together. You tried to pull one quark loose, and instead you made new matter, and the new matter immediately paired up so that no quark is ever left alone. Picture trying to snap off just the north pole of a bar magnet. You cannot. The instant you break the magnet in two, each piece grows a fresh south pole and a fresh north pole at the broken faces, and you end up with two complete magnets. You can never isolate a single pole. The strong force works the same way. Break the bond, and new ends appear to keep every quark partnered. A lone quark is as impossible as a magnet with only one pole. This is why quarks are locked away forever, a state physicists call confinement. You can never hold a single quark in your hand. Pull one out, and you spend your energy making new quarks that immediately pair up, so a solitary quark never appears. They are prisoners for life, and the prison rebuilds its own walls the moment you attack them. And now the storm inside the proton makes complete sense. The quarks are trapped in a space so small that they must race at nearly the speed of light. The strong force binding them holds enormous energy stored in those tight tubes of force stretched between them, and all that energy of motion and binding, by the rule that energy has weight, is the weight of the proton. The missing 99%, the weight of nearly everything you are, is the energy of quarks imprisoned by a force that will not let them go. But this raging prison was not always sealed. There was a moment, in the first breath of the universe, when it was too hot for the prison to hold, and the quarks ran free. We have recreated that moment, and doing so meant building a piece of the early universe on Earth. The strong force locks quarks away for life, but there is one condition under which even this unbreakable prison fails, and the quarks run free. Heat, enough heat, and the prison melts. And in the first slivers of time after the universe began, the whole cosmos was that hot. Wind the clock back to the very beginning. In the first tiny fraction of a second after the universe burst into being, everything was unimaginably hot, hotter than the center of any star, hotter than any furnace that has existed since. At that ferocious temperature, the strong force could not hold quarks together at all. The heat was too violent. The prison walls could not form. So there were no protons, no neutrons, no atoms, nothing built from bound quarks. There was only a searing, universe-filling soup of quarks and their messengers, all mixed together, all racing free. This state of matter, this quark soup, existed for only the briefest instant at the dawn of everything, before the universe cooled enough for the strong force to grab hold and slam its prisoners into place. For a long time, it was purely a story about the ancient past, a state of matter that had not existed since the universe was younger than a heartbeat. Then scientists decided to make it again, on Earth, on purpose. In the most powerful colliders ever built, physicists took heavy atoms, packed with protons and neutrons, and smashed them together at nearly the speed of light. The collision concentrated a staggering amount of energy into a spot smaller than a single atom, driving the temperature to trillions of degrees, hotter than the heart of any star, hot enough to melt protons and neutrons back into the free quarks and messengers of the early universe. For the tiniest flicker of time, in a space smaller than an atom, they recreated the soup that filled all of space before matter as we know it existed. The soup lived for far less than the blink of an eye, an almost inconceivably short instant, before it cooled and the quarks snapped back into ordinary particles. But it was there. Scientists made a droplet of the newborn universe, studied it, and watched ordinary matter freeze out of it as it cooled. The same way matter first formed in the beginning. Picture ice locking water molecules into a rigid, frozen structure. Heat the ice and it melts, and the molecules that were trapped in place flow freely again. The strong force is like the cold that freezes quarks into protons. Heat things enough, and the freezing fails, and the quarks flow free as a liquid, the quark soup. The colliders reheat a speck of the universe until its matter melts, then watch it freeze again. This is one of the most astonishing things our species has done. We took the conditions of the universe's first instant, before any atom existed, and rebuilt them in a machine over and over, learning to read the story of creation by running it again in miniature. And it tells us exactly how the weight of the world switched on in a single moment near the beginning of time, when the whole universe crossed a threshold, and the storms inside matter ignited across all of space at once. We have seen that almost all the weight of ordinary matter is the energy of quarks trapped inside protons and neutrons, storms of imprisoned energy that show up on the scale as heaviness. But there was a moment when those storms did not yet exist, when the quarks ran free in the hot soup and no protons had formed. So there was a specific instant, early in the life of the universe, when the weight of the ordinary world switched on, and we can pin down when. Then the universe expanded and cooled, as it has been doing ever since. And at a certain moment, just a few millionths of a second after the beginning, the temperature dropped low enough that the strong force could finally take hold. All across the universe, almost at the same instant, the free quarks were swept up and locked together, confined into protons and neutrons for the very first time. The prison walls formed everywhere at once, the storms ignited, and the weight of matter, which had waited invisibly in that hot soup, suddenly had somewhere to live. And in that same moment, nearly all the weight of ordinary matter switched on. Before it, the quarks existed, but the trapped, energetic systems we call protons and neutrons did not, and so the weight that comes from their confinement did not yet exist. After it, the universe was suddenly filled with protons and neutrons, each one a tiny sealed storm of strong force energy, each one carrying the weight that we have spent this whole journey chasing. Take in what that means. The weight of every atom in your body traces back to a single instant, just millionths of a second after the beginning of everything, when the cooling universe first let the strong force cage its quarks. The weight was not built up slowly, particle by particle, over the long ages that followed. It was born almost all at once, in the universe's first breath, when confinement switched on across all of space, and the energy of the strong force became locked into permanent weight. Picture a vast lake of liquid water, cooling degree by degree, and then at one instant crossing the freezing point, so that across the entire lake, almost at once, the water locks into ice. Before that instant, flowing liquid. After it, solid ice, everywhere, together. The birth of matter's weight was a freezing like that, spread across the whole universe in a single cold moment. The quark soup froze into protons, and the weight of the world appeared. So the heaviness of everything you know is nearly 14 billion years old, forged in the opening heartbeat of the cosmos, and it has been raging quietly inside every proton and neutron ever since. When you feel your own weight, you are feeling energy that was locked into matter in the universe's first instant, still trapped, still storming, all these ages later. We have followed matter all the way down, from the solid marble to the raging storm, from the field to the vacuum to the birth of weight itself. Only one question remains, the deepest one of all. If everything is ripples in fields, then what are the fields themselves made of? And here, at the very bottom, even our best knowledge runs out. We have reached the bottom floor of everything we know. Matter is not made of tiny marbles. It is made of ripples in invisible fields that fill all of space. The proton is a storm. Weight is trapped energy. Empty space boils. Particles spread into clouds of possibility and link their fates across the galaxy. Every strange thing we have seen flows from one idea, that the fields are the true bedrock of reality, and everything else is their trembling. So now ask the obvious question, the one a curious child would ask. If everything is ripples in fields, then what are the fields made of? What is the water in the invisible ocean? What lies beneath the bedrock? And here, at the very bottom, our knowledge runs out. The honest answer is that we do not know. The fields are, as far as our best theories go, the ground level of reality. They are not made of anything smaller that we have found. They are the starting point, the thing everything else is built from. And beneath them, our map goes blank. We can describe the fields with breathtaking precision. We can predict how their ripples behave to more decimal places than almost anything else in science. But when you ask what the fields themselves are, made of what deeper substance, we have no answer. We have only the fields. This is not a failure to be ashamed of. It is the frontier. Every map of reality has an edge, a place where the known gives way to the unknown. And for us, right now, the fields are that edge. We have peeled back layer after layer, atom to nucleus, to proton, to quark, to field. And at the field we have hit the deepest thing our instruments and theories can reach. Whether there is something beneath it, some finer structure, some hidden foundation, is one of the great open questions, and some of the boldest ideas in physics are attempts to guess what that deeper layer might be. Picture explorers who have sailed to the edge of every known sea and mapped every coastline until they reach one final shore beyond which their maps show only blank space. They can describe everything up to that shore in perfect detail, but past it, they have only guesses and the horizon. The fields are that final shore. We have charted everything up to them. Beyond them lies the unmapped deep. Some scientists suspect the fields might be ripples of something deeper still, that space and matter and even the fields themselves might emerge from some more fundamental thing we have barely begun to imagine. These are among the hardest and most exciting questions anyone can ask, and they are being worked on right now at the very edge of human understanding. We may find a deeper layer. We may find that the fields truly are the bottom. Nobody yet knows. What we do know is enough to change how you see yourself completely. Because if you are made of ripples in fields, then the old picture of you as a collection of tiny solid particles, little grains of stuff assembled into a body, was never true. You are something far stranger and far more wonderful. To finish this journey, we have to put the whole picture together and look, at last, at what you truly are. Before we assemble the final picture of what you are, there is one last wonder to face, and it is the strangest inheritance of everything we have learned. The emptiness inside you, and the emptiness of all space, is not empty. It hums. And that hum may be the largest hidden thing in the universe. Remember that the fields can never fully rest, that even in the coldest, emptiest void, they keep trembling, forbidden from perfect stillness. That endless trembling carries energy, the leftover shiver of every field in every point of space, and space is vast beyond comprehension. So if you add up that faint trembling energy across all the emptiness in the universe, across the immense dark gulfs between the stars and the far greater voids between the galaxies, the total should be staggering. This leftover energy of empty space has a strange power. Unlike matter, which pulls things together, this energy of the vacuum appears to push space itself apart. And astronomers have discovered something that fits this eerily well. The expansion of the universe is speeding up. Galaxies are racing away from one another faster and faster, driven by some unseen energy woven into empty space itself, an energy that grows in total as space grows, pushing ever harder. We do not fully understand this energy. It is one of the deepest mysteries in all of science, so mysterious that scientists gave the unknown push a placeholder name that simply marks our ignorance. But its effect is real and measured. The emptiness is winning. The trembling of the void, or something very like it, is pushing the entire universe apart, and it will keep doing so, carrying the galaxies away into an ever colder, ever emptier future. Sit with the scale of this. The busiest, most powerful thing in the cosmos may be the energy hidden in emptiness itself, the same restless trembling that boils up virtual particles and pushes those metal plates together in the laboratory, blown up to the size of the whole universe. That trembling appears to be steering the fate of everything, deciding how the cosmos ends. Picture a still, dark pond that seems calm and dead, but is secretly rising, its hidden pressure slowly pushing its own banks outward, widening itself without end. Empty space is that pond. Its quiet trembling holds a pressure that is spreading the universe apart, faster every moment, an ocean of emptiness swelling toward an endless dark horizon. So, the void we began by calling nothing has turned out to be the master of everything. It flickers with ghost particles. It presses on solid matter. It gives birth to the ripples that become all things. And on the largest scale of all, it may hold the energy that decides the future of the universe itself. The deepest layer of reality, the trembling emptiness beneath all matter, is anything but empty and anything but quiet. We have traveled from the solid marble in your head all the way to the humming void that fills the cosmos and drives its fate. Now, at last, we can gather everything we have found and answer the question we started with, the question hiding behind every chapter. What are you, truly, at the deepest quantum layer? And the answer will not feel like an answer about physics at all. It will feel like an answer about what it means to exist. We began with a simple picture. You are made of tiny, solid particles, little grains of stuff, assembled into a body. Everything we have learned demolishes that picture. So let us replace it with the truth. And the truth is stranger and more beautiful than the marble ever was. You are a pattern of ripples in invisible fields that fill all of space. Go through it piece by piece, because every word of that sentence has been earned. The particles in your body are ripples in fields, not grains of stuff. The weight of you is almost entirely trapped energy, storms of imprisoned force raging inside every proton, energy wearing the mask of solid matter. The small remaining weight of your fundamental particles is a hum set by a field that switched on in the universe's first instant. The solidity you feel, the firmness of your own hand, is a quantum rule forbidding your electrons from sharing states. A refusal to crowd felt as resistance. And the emptiness inside your atoms, which is nearly all of you, is not empty at all, but a trembling, boiling sea. So the thing you call your body is a pattern, a particular arrangement of ripples and storms and rules, holding its shape while the actual material flows and flickers beneath it. Your atoms trade electrons with the air. The virtual particles inside you appear and vanish trillions of times over. The quarks in your protons race and swarm without pause. You are not a fixed object made of permanent grains. You are a standing pattern, a shape that persists, like a wave that holds its form while the water rushes through it. Picture a wave rolling across the ocean toward the shore. The wave is real. It has a shape, a size, a speed, a presence you could point to, but it is not made of any particular water. The water it is passing through right now is not the water it passed through a moment ago. The wave is a pattern moving through the sea, and the sea flows through the pattern. You are that wave, the fields are the sea, and the pattern that is you moves through them, holding its shape, while the deep material of reality flows on beneath. This is not a poetic exaggeration. It is the plain reading of everything physics has discovered about matter. At the deepest layer, there are no little balls of you. There is a pattern in the fields, humming, storming, trembling, holding together as you, for as long as you live. And that pattern is ancient. The fields you are rippling in have existed since the beginning of the universe. The weight you carry was forged in the first millionths of a second of time. The electrons humming in your brain are ripples in the very same field that ripples in the farthest stars. You are not separate from the cosmos, a small, solid thing placed inside a big empty one. You are a pattern in the same fields that make up everything, woven from the same trembling oceans that fill all of space. We have one final step to take, to stand back and see the whole picture at once, from the marble to the ripple, and to feel what it means that the solid world, the most real and solid thing you know, is built from something that is barely there at all. Stand back now and look at the whole journey at once. We started with the most obvious belief a person can hold, that the world is made of solid stuff, hard grains of matter assembled into everything you can touch. And step by step, that belief has dissolved in our hands, replaced by something that sounds impossible, yet is the deepest truth we know. The solid world is built from things that are barely there. Follow the chain of almost nothings. Your body is made of atoms, and atoms are almost entirely empty space, a tiny, heavy center in a vast void. That tiny center, the proton, is a storm of racing quarks and swarming ghost particles, weighing 100 times more than its actual pieces, because nearly all of it is trapped energy rather than any solid grain. Those quarks and every other particle are ripples in invisible fields, disturbances in oceans that fill all of space, and the emptiness around them boils with particles flickering out of nothing, trembling with an energy that can never fully rest. At every level we looked, the solidness melted away. There was no final hard grain, no bottom marble, no little nugget of pure stuff. There was empty space, and energy, and trembling fields, and rules, all the way down. The most real and solid thing you know, the physical world you can knock on and lean against, is built from emptiness, motion, and trapped energy. The substance of the world, at its root, is barely substance at all, and yet the world is real. The table holds your weight. The mountain does not crumble. You are here, solid and warm and alive. This is the wonder at the heart of everything we have found. Solidity is real, and it is built from almost nothing. The firmness you feel is a quantum rule. The weight you carry is trapped energy. The stuff you are made of is ripples in fields, all of it barely there, and all of it holding together into a world you can live in and touch and love. Picture a rainbow arched across the sky, vivid and clear, so present you feel you could walk up and touch it. Yet it is made of nothing but light and water and angle, a pattern with no substance you could ever grasp, and if you walk toward it, there is nothing there to hold. The solid world is like that rainbow, only it does hold together, firm enough to build a life on, though it is woven from things as insubstantial as trembling fields and trapped light. That it feels solid at all is the greatest magic trick in the universe, performed in every atom, without pause, since the beginning of time. This is what physics has truly discovered about matter, and it overturns the belief we all start with. We are taught that matter is made of tiny bits of solid substance. When we look as closely as it is possible to look, we find that the substance is not there. The weight lives in the storms. The particles are ripples. The emptiness boils. The solid world is a pattern of energy and rules, humming in fields that fill all of space. And so, at the end of this long descent into the smallest layer of reality, one truth remains to be spoken plainly, a truth about you and about everything, and it is the most astonishing fact this whole journey has uncovered. We asked a simple question at the start: what is matter made of, at the deepest layer? We were wrong about the answer, all of us, from the ancient thinkers to the picture in your own head, and the true answer is stranger and more beautiful than anyone imagined. Matter, at its root, is trapped energy given the face of solid stuff. Gather everything we have found into a single truth. The weight of a proton, which is nearly all the weight of every atom, and so nearly all the weight of you, comes overwhelmingly from energy. The energy of quarks racing at the edge of the speed of light, imprisoned in a space too small to picture. The energy of the strong force, stored in tight tubes stretched between them, raging without pause. That energy, by the deepest law of nature, has weight, and that weight is most of the weight of the world. So the heaviness of everything you know is, in the truest sense, the weight of trapped energy. The mountains, the oceans, the planet, the stars, and your own body, all of them are heavy, mostly because of energy locked inside their protons. Energy that cannot escape, storming forever in its tiny cage. The solid, substantial world is bound energy wearing the mask of matter. It is, in a real sense, trapped light given the weight of stuff. And this trapped energy is old beyond imagining. It was locked into matter in the first millionths of a second after the universe began, when the cooling cosmos let the strong force cage its quarks across all of space at once. The weight you carry through your day was forged in the opening heartbeat of the universe, nearly 14 billion years ago, and it has been raging quietly inside every proton and neutron ever since. In every atom that has ever existed, you began this journey picturing yourself as a collection of tiny solid grains. You end it knowing the truth. You are a pattern of ripples in fields that fill all of space, given weight by storms of ancient trapped energy, held solid by rules that forbid your particles from crowding, humming in the same oceans that ripple in the farthest stars. The emptiness inside you boils. The weight inside you is fire, caught in a cage since the beginning of time. And the solid, ordinary world you touch every day is the greatest wonder there is. A universe of substance built from almost nothing, holding together against every expectation. Picture a single ember from the first fire ever lit, still glowing, sealed inside every particle of you, never cooling, never dying, burning quietly since the universe was born. That ancient, trapped fire is your weight. It is the weight of everything. The strong force made solid, energy given a face, the universe showing you, in every atom of your own body, that matter and energy are one, and that the solid world is built, from top to bottom, from the tireless, trapped, and ancient fire of the force that binds the smallest things together. We were wrong about matter. It was never solid stuff at all. It was storms and ripples and trapped light, humming in the dark, all the way down, and now you know what you truly are.